Okay, today we're going over 8.3 logarithmic functions as inverses. So let's take a look at a couple things here. First thing we're going to learn is how to convert it, and we need to know what it's going to look like as an exponential form, and then what it will look like as logarithmic form. So here's the equation, and we're going to have y is equal to b to the x. This is exponential form right here. And converting it, we're going to have log base b. So we can remember your base b here. It's like a subscript, and your base b is here as well. Of y is equal to x. And x is the exponent over here. So you can just remember this as log equations are equal to the exponent. So let's go over converting some of them and rewriting it. So the exponent x in the exponential expression b to the x is the logarithm in the equation log base b of y equals x. So we're just converting one or the other, exponential form or logarithmic form. Okay, so if we want to write, we all know that 5 squared is 25. But we now want to write it in logarithmic form. So we have our equations right here, and we can just go by those. And we're going to use, let's see, the base b is 5 here. So if it helps you, you can write it out. B is equal to 5, x is equal to 2, and y is equal to 25. If that's helpful, you can do that. Or you can just look at this equation. So you have log base b, your b is 5. Log base 5, and it's a subscript, so write it smaller. Of y, so we know y is 25 here. 25 is equal to x is your exponent, which is a 2. And that is writing it in logarithmic form. And we'll see later on why we need to know both exponential and logarithmic form. So let's go over some more. And let's just write down those two forms so that we have it as a reference there. So we have y is equal to b to the x. That's exponential form. And log base b of y is equal to x. So we'll rewrite this. Right now this is in exponential form. We're going to write it in logarithmic form. So we have log base 3 of 729 is equal to your exponent x, which is a 6. This one here is log, your base is a half. Base of a half of 1/8 is equal to 3. And finally, we have log base 10 of 1 is equal to 0, which we're going to later on learn that log base 10 is actually called a common log. And we'll go over that in a little bit. All right, moving on, we're looking at evaluating logarithms. So we need to evaluate log base 8 of 16, and we want to know what that's equal to. So we'll just say it's equal to x for now, because we don't know what it is. So what we're going to do is, since it's in logarithmic form and we need to solve it, we're going to now convert it to exponential form. So using our form, we know that 8 is your base. Log forms are equal to the exponent, so 8 to the x power is equal to 16. Okay, so now what you're going to do is you're going to get these to be the same base. So we're going to say, what number can I make this 8 and this 16 be? And that's going to be a 2, because 2 cubed is the same as 8, and 2 to the 4th is the same as 16. And then we need to remember some of our exponent properties here. If there's exponent inside and outside, we multiply it. So 2 to the 3x is equal to 2 to the 4th. So once we get to the same base here, the 2's are the same. Now all you're going to do is you're going to set your exponents equal. So we have 3x equals 4, and then you'll solve for x. Divide both sides by 3, and therefore x is equal to 4/3. So log base 8 of 16 is equal to 4/3. Okay, moving on here, we're going to try some more problems like this. And we could start with this one here. So the first thing that we did was we set this equal to x. And now I'll convert it. So I have 9 to the x power is equal to 27. Converting them so that they have the same base, I can make both of them have a base of 3. So this one is 3 squared to the x, and then that's equal to 3 to the 3rd is the same as 27. Then once you have the same base, you set your exponents equal. That's an equal sign, sorry. And then you divide by 2. And x is equal to 3/2. So log base 9 of 27 is equal to 3/2. Okay, moving on here. This one will set equal to x. I have 64 to the x power is equal to 1/32. So we have a couple options here, but as you can see, one of them is a whole number and one of them is a fraction. So we want to make either both of them whole numbers or both of them fractions. So I'm going to make this one a whole number by bringing this 32 up top, and in order to do that, I'm just going to make it to the -1 power. Because that's the same thing. 32 to the -1 is the same as 1/32. Okay, so now I need to think of what can I make my values of x be. So I can say, all right, well, I can make both of them have a base of 2. And this is going to be 2 to the 5th power is 32, because I know 2 to the 4th power is the same as squaring it twice. 2 squared is 4, 4 squared is 16, and then times another 2 is 32, so that's 2 to the 5th, which means multiply by another 2 and you'll get 64, so this is 2 to the 6th power is 64, so this is the same as writing 2 to the 6x is equal to 2 to the -5 here. Okay, and then we can convert it where we have the same base. Once we have the same base, we set the exponents equal to each other. We can divide both sides by a 6 now. And we get x is equal to -5/6. All right, one more here. We have log base 10 of 100. We'll say, okay, let's set that equal to x. And we have 10 to what power is 100. So sometimes you'll have easier ones where you can just find out the answer. 10 to what power is 100? But if you don't see it, then we'll just make them both have the same base. 10 squared is 100. And then now that we have the same base, we have to set the exponents equal, and x equals 2. All right, moving on here. We're going to be looking at a common logarithm. So common log is using a base of 10, base 10 here. So you can write the common logarithm log base 10 of y as log of y, which means if you do not see a base, it's known to be a common logarithm. It's kind of like when we're used to having, okay, x to the first, we don't have to put that exponent 1, we just know that x to the first is an x. So when we write log base 10 of y, we don't need to put this base anymore. There's no base written in, then it's just known that it's a common log, and it's just log of y is how it will be written. Okay, so a logarithmic function is the inverse of an exponential function. They're inverses of each other, and we've gone over inverses before, and we know that when we're looking at inverses, we know that we switch x and y. That's what it's doing when you're finding inverses. You're switching x and y. So if we have y is equal to 10 to the x, that's the same as writing log base 10 of y is equal to x. These are equivalent forms. This is exponential form and this is logarithmic form. These are the same thing. So it has an inverse of, we said the inverse is switching x and y. So I could switch these x's and y's, the x and y here, and the inverse is log of x equals y. I just switched the x and y. So the equivalent here for that one is 10 to the y is equal to x. And this is your exponential form. So when we're graphing those, we're going to graph these. And now if you notice, we have y in our exponent. So we have x and y. X and y. And if you notice here, y is now in the exponent. So what's going to happen is it's going to now be easier to plug in y values and then solve for x. So if your y is in your exponent, you're going to plug in values for y. So let's do that. I can do -2, -1, 0, 1, 2. That would be kind of big. Okay, so now I'm going to evaluate this. Because x, we know, is equal to 10 to the y. So I have 10 to the -2 is equal to 1 over 100. Okay, 10 to the -1 is equal to 1 over 10. 10 to the 0, anything to the 0 is a 1. And 10 to the first is 10. All right, so now I can graph those here where I am going to look at this and say, okay, when I graph these 1 over 100, -2. If I try and graph that, we're going to see that I'll have 1 over 100, it's going to be really close to here, and then -2 down here. Okay, make that a little bigger. There we go. 1 over 10, -1 is right here, about. Okay, we're going to have 1, 0. 1, 0 is about right here. And 10, 1. 2, 3, 5, 6, 7, 8, 9, 10. 10, 1 will be about right there. Okay, so now if we see, instead of it having an asymptote of y equals 0, now we can see, oops, my graph is off a little bit, sorry, that now we can see that it's now approaching, we should see that it's approaching now the y-axis, which is right here, x equals 0. Okay, so now we could see that x equals 0 is now it's going to have a vertical asymptote. So when you have logarithms that have it as y equals log, or in this case 10 to the y is equal to x, these are equivalent statements. These two right here are equivalent statements. It will look something like this, which is a logarithmic function, and it will have a vertical asymptote of x equals 0. Okay, so moving on here, let's do another one. We know that another way that you can do it is by graphing both of them and then reflecting it over the y equals x line. So you can also do that. Or you can graph one of them, y equals 2 to the x, and then you can switch x and y. Okay, so it says to graph y equals log base 2 of x. So we can just go straight to, we know that y equals log base 2 of x. That is the same as writing 2 to the y is equal to x, right? 2 to the y is equal to x. That's rewriting it in exponential form. So we just said that if it's written in this form, I'm going to plug in values for y. You always want to plug in the values for your exponent and then solve for your x, or the other variable. So we have -2, -1, 0, 1, 2, and 3. So I have 2 to the -2 is 1 over 2 squared, which is 1/4. Okay, I have 2 to the -1 is 1/2. I have 2 to the 0 is a 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. So solving here, I know that when it's in this form, I just went over that your vertical asymptote, now we have vertical asymptote, is x equals 0. So if you want to go ahead and draw that in first, you can do that. Here's my x equals 0, and then we're going to also show the translations of that in a minute, in a little bit. So we have x equals 0 here. And then plotting these, I have 1/4 -2 is around here, down there. 1/2 -1, 1/2 -1, 1 0, 1 0, 2 1, 4 2, 4 2, and 8 3, 8 3. Right here. Okay, and then we can draw this in here, showing that it's going to be approaching my vertical asymptote. And that graph is a little bit better. And that's how we graph logarithmic functions. Okay, moving on here. So let's just look at a few things here. So we know that when we're looking at these, the function of y equals log base b of x is the inverse of y equals b to the x. We know that because if I write this out, I can say this is my base b. Log equations are equal to your exponents, y. So b to the y is equal to x. These are equivalent statements here. Okay, so the inverse is switching your x and y. So that's the inverse of that. And if we wanted to write this in logarithmic form, I'd write log base b of y is equal to x. So those are inverses. Since 0, 1, and 1b are points on the graph of y equals b to the x, because if you plug in 0 for x, b to the 0, anything to the 0 is a 1. That's how we got 0, 1. And if I plug in 1 here, b to the first is just b. So you get a b there. Then that means we switch x and y. That's what we said we do for inverses. We switch x and y. So therefore, we'll switch these. 1, 0 and b1 are going to be points on the graph of y equals log base b of x, because that is the inverse. So we went over this a little bit before when we were graphing them, but it says since the x-axis is the asymptote of the graph of y equals b to the x, the y-axis is now the asymptote of the graph of y equals log base b of x. And then we're going to have our translations, like always. So we know that since we're going to have our translations here, we know that in this form, this is the equivalent to saying b to the y is equal to x. B to the y is equal to x. And we just said for this one that your y-axis, or x equals 0, is your asymptote there. Okay, so now if you have x equals 0, which is a vertical line, since that's a vertical line, if I move left and right, that's what's going to change my asymptote. So now x equals h is going to be your asymptote for your translation. Okay, your domain there if you saw before in the previous graph, these are only having positive x values here, and it's not including 0 because that's the asymptote. So your domain is x is greater than 0. For this one, if we move h units left to right, that just means that we're going to have our domain is now x is greater than h. For the range, it's going up and down, so it's going to be all reals for both of them. Okay, so let's do a translation here. So the first thing you're going to do is graph the parent graph, which is going to be y is equal to log base 6 of x, which we can change from logarithmic form to exponential form, which is 6 to the y is equal to x. So since my y is going to be my exponent, then that means I'm going to plug in values for y. So I could do that. I'll plug in, let's say, a -2, -1, a 0, and a 1. Okay, so I'll have 6 to the -2 is equal to 1 over 6 squared, which is the same as 1 over 36. Next one, I'll have 6 to the -1 is 1 over 6 to the first, which is the same as 1/6. 6 to the 0 is the same as 1, and 6 to the first is 6. Okay, so I can graph that. Let's go ahead and graph that, and also make sure we put in our asymptote. So I have x equals 0 right now. So I have x equals 0 as my vertical asymptote. And now I'll graph those. So I have 1 over 36 -2 down there. I have 1 over 6 -1. I have 1, 0, 6, 1. 6, 1, right there. Okay, so now I'll sketch this in. And continue my graph. Okay, so now if we take a look at our translation, what we're going to be looking at is this one right here. Since it's x minus h, now I know that x equals 2 is now going to be my vertical asymptote, which also means that we're going to be going right 2 units and 3 up 3 units. So if I'm going right 2 units means that I'm going to go add 2 to all of the x's, and up 3 units means I'm going to add 3 to all of my y values. So let's recreate this chart here, x and y. So I'm going to have plus 2, so 2 and 1 over 36, 2 and 1/6. 2 plus 1 is a 3, and 2 plus 6 is an 8. For this one here, I'll have 3 minus 2 is a 1. Okay. 3 minus 2 is a 1. 3 minus 1 is 2. 3 plus 0 is 3. And 3 plus 1 is a 4. Alright, so then we'll graph that, and we know that we first need to put in our vertical asymptote, which is x equals 2. So put that in first. X equals, hold on. So x equals 2 is right here. And so that's x equals 2. And then we can graph that in. So I have my table down here, 2 and 1/6, 1. 2 and 1/6, 1. Right there. I have 2 and 1/6, 2. 2 and 1 6, 2. That's right here. I had 3 3 and 8 4. So 3 3, 3 3, and 8 4. Eight, 4. Okay, and then we can sketch the graph of that. Something like that. And that is how we graph logarithmic functions. Thanks for listening.